Okay, we are at page 39. Let us prove the linearity of Laplace transform. So we know that the Laplace transform of x1t becomes x1s. The Laplace transform of x2t becomes x2s. Linearity tells us that a1, the scaling of x1t by a1 is the scaling of x2t by a2. This is the resultant effect. First is that the signal, when they sum, we still can analyze each of them individually like this. Now, why is this so? So let us examine the Laplace transform equation directly and show that this is true. So here we are doing the bilateral transform here. You will apply equally if it is single-sided. So a1 x1t plus a2 x2t, this is the original signal, and we are multiplying by e minus st. We distribute, we open up the bracket and distribute, and then this is what we can find for the first expression. This is what we can find for the second expression. We note that this expression is simply a1 x1s, and this expression is simply a2 x2s. That's it, we prove. Okay, so pictorially, of course, it looks like this. We have a1 x1t, a2 x2t. We can do each of them individually. We get this for each of these a1 x1t, a2 x2t. Then we put it back here again. Alright, so that's the idea of linearity. Time differentiation. Well, time differentiation says that if my signal is x of t and x of t give me x of s, what does the differentiation of the signal dx dt gives us? And interestingly, it gives us back x of s multiplying by s minus a constant value, the initial value, the small x, which is the time domain representation equation, and we insert time 0 there. So this is a very important result because, I mean, you know, if the expression of x of t is complicated, differentiation is also complicated. But in the Laplace domain, if we already have x of s, the differentiation is simply pushing s multiplied by s of s minus a constant. That's it. So it is much simpler to do differentiation in the Laplace domain. Alright, why is this true? Okay, let's go from the beginning. The Laplace transform of dx dt is, of course, now we are doing it with the causal, the right hand side. We are taking about the unilateral. Okay, just to make our life a little bit easier. But I guess in this particular case, we are going to only use the unilateral transform. Alright, so we're going to integrate from 0 to infinity. Here, it marks as 0 minus. Time is just a little bit on the left hand side of the origin. The function that we are trying to perform Laplace transform, which is dx dt, e minus st dt. Now, when you reach here, to proceed, you must know something called integration by parts. And then in integration by parts, you have to determine your u and your v. So I can tell you now that your u should be e minus st. So this is your u. And this is your v. Or I should say this is your dv. Okay. So once you have determined your u and your dv, you can, of course, given your u, you can find du. So you simply take this expression and perform du, okay, which is this guy. If you have dv as this, therefore you can quickly find the inverse of dx dt, which is xt. So this is v. So answer is, to perform integration by parts is uv minus integral v du. Then you can solve. Alright, see my answer here. And you realize that out pops this x of s, or I should say f of s later on. Okay, look at this expression, and this is what we find. So this term will give us x of 0, and this term, the second term, will give us sfs. Of course, typically we just simply use this result. The Laplace transform of a differentiation is simply s times the x of s plus, I should say minus, should be a minus sign here. Okay, so notice the mistake here. Alright. You can of course generalize this for nth order differential equations. And I do the second order for you here. d2x over dt square is equals to s square x of s minus s x of 0 minus x prime of 0. Okay? Alright. So let's move on to the example 1 using the property of the differential equation to solve for a RL circuit. So this is a typical RL circuit. We have a voltage source, and we have a switch that closes in time 0, and we have a resistor here, and we have an inductor here, and we have a current here. Okay, now, so why is this a differential equation? Is the voltage drop across the VL is L di dt. So immediately you can see a differential equations coming out. The voltage drop across R is IT multiplied by the resistance, and by the Kirchhoff's voltage law, the sum of voltage drop across the entire circuit is 0. So what happened is that we will see that this is the voltage drop across the inductor, L di dt, voltage drop across the resistor, I times R, as well as the voltage source. Now the word UT here stands for unit step. So what we are saying is that in time equals to 0, we close the switch. So the voltage happens only at time 0. So we have this differential equation, and then we are trying to solve for, of course, I of t. What is I of t? Now, so very quickly you realize that we apply the differentiation property. Di dt is s of is minus I0. Sometimes we don't use the plus because it's understood whether it's plus or minus. Now, so what about L? L is a constant here, so L drops out outside. What about R and I? Again, R is the resistor, is a constant, so R drops out here. IT becomes IS, and V is a constant, so V is a single number. The UT is important because the Laplace transform of UT is equals to 1 over S. So that's why we get this expression here. So now we converted our differential equations into an algebraic equation. And of course, we are going to manipulate it around to move IS on the one side, and then the rest of the expression on the right hand side, which is V over S Ls plus R. Now, in this form, we have a problem because there's no lookup table. We cannot find a lookup table that converts this form into IT. So what we do is by partial fraction expansion, and you have to read out partial expansion to break this complicated looking function into small parts like this. So by partial fraction expansion, we can find the value of A and the value of B and so on. So what happened is that now when we have, in this particular example, they solve for you, small a is equals to V over R, small b is equals to V over R, and things like that. Once we have this, then it's very easy to perform inverse Laplace transform because there's a table for this. So I of t is equals to V over R, and 1 over S becomes ut. That's the idea. What about this one? Minus, okay, so the minus comes here. And then we have V over R, because that's just a simple constant. 1 over S plus RL becomes E minus R over LT. And then you can group the V over R together, and you have 1 minus E minus R over LT UT. So this is the answer here. So in this example, we have a simple RL circuit. We learn how to form the RL circuit as differential equation. And then we convert these differential equations using the property of differentiation to get the algebraic form. We manipulate the algebraic form to get the equations that we want. And then by partial fraction, we express the complicated expression into individual little parts that have lookup table, and we go use the lookup table, and voila, that's the answer. Okay, with that, I think that's a whirlwind tour of at least using the property of differential equations for Laplace transform, or using Laplace transform on differential equations. Thank you.